Hello everybody, welcome back to another AP Calculus ABC video. This is lesson 5 of unit 6, behavior of accumulation functions. So let's recall, if a function has a relative minimum, then that means that its derivative has to equal 0, right? We have to have our critical points, and the critical points from the left, it goes from negative, and to the right, it goes positive. For relative maximum, again, you find the critical points of a function, and you do a sign chart to see where the graph goes from negative, or in this case, it's a maximum, so from positive to negative. Concave up, you're going to find the second derivative of a function, and then you're going to do a sign chart, and any interval that is positive is concave up. Same thing for concave down, but whenever the second derivative is negative, then it is concave down. If a function is increasing, then g prime, or the function's first derivative, is going to be greater than 0 or positive. If a function is decreasing, that function's first derivative is less than 0 or negative. Points of inflection. So if we find the second derivative, and we're going to see when the second derivative changes signs. Alright, so hopefully that covers up everything here. Let g of x equal the integral from a to x, f of t dt. With the graph of f shown above and a is a constant, find the x values of g regarding each of the following conditions. So we can use the fundamental theorem of calculus. And then we know that the graph here is the graph of f, and we're given the equation of g. All right, so relative minimum. Well, how to find a relative minimum? We find critical point, and then when the critical point changes from negative to positive. How do we find a critical point? First derivative equal to 0. So let's do that up here. So g prime of x, derivative and integral cancel, so we're left with f of x. So when is g prime of x equal to 0? That's going to be when f of x is equal to 0. Okay, now, since we're finding the relative minimum, we're going to look for the part of the graph where f of x equals 0, but it goes from negative to positive. So I see that would be 2 right here, right? Because our graph goes from negative to positive, and it touches 0. So at x equals 2. Maximum, same thing, but we're going to find when our graph goes from positive to negative. So that would be right around here. That is, can say 6.5. Okay, concave up. Concave up, concavity, we need to find a second derivative. So our second derivative, so first derivative we know is g prime equal to f of x. Second derivative is g prime of x equal to f prime of x. So knowing that g double prime of x equals f prime of x, let's find the concavity. So it is concave up. So, okay, right. So concave up means that g double prime of x has to be greater than 0. So that means that f prime is going to be greater than 0. So f prime is the slope, right? So we're going to look at the slope. Well, I can see that the slope is positive here, and it's positive here as well. So we can say that our graph is concave up from negative infinity to 4. And it doesn't look like it has a positive slope for the rest of the graph. Concave down is when f prime is less than 0, right? Because g double prime has to be less than 0. So our slope is negative here. Right here, be careful. This is 0. That has a slope of 0, so we wouldn't include that. But here it is negative. So we're going to say from 4 to 5 and 6 to infinity. When is g increasing? If a function is increasing, then the function's first derivative has to be equal. It has to be greater than 0. It has to be positive. So we're going to find when g prime is positive. Well, we know that g prime is f, right, from the fundamental theorem of calculus. So when is f greater than 0? All right, so we're going to look at the graph. When is f positive? That's going to be from 2 to 6.5. 2 to 6.5. When is when is g decreasing? So g is decreasing when g prime is less than 0 or negative. That means that f is less than 0 if g is decreasing. So we're going to look at the graph and we can see that it is decreasing. It is negative from negative infinity to 2 and 6.5 to infinity. All right. Point of inflection. Point of inflection occurs when a function's second derivative changes signs. So when does g double prime change signs? G double prime changes signs. Well, we know that g double prime equals f prime. So when does f prime change signs? Or in another word, when does the slope go from positive to negative or negative to positive? So from here we can see it's positive, positive slope, and right here we hit 0, right? So from the right, now it's negative slope. So we can conclude that at 4, our g double prime changes signs because our f prime changes signs, right? So x equals 4 decreases, stays the same, decreases. So it's only going to be x equals 4. Okay, if g of 3 equals negative 2, what is the maximum value of g on the interval 3 to 7? Okay, well, we're given an initial condition. G of 3 equals negative 2. What is the maximum value from 3 to 7? So it's really important to take note of from 3 to 7. So let's erase this. So from 3 to 7 is right here to here. So we have a positive area under the curve, and then we have negative area. But since we're asked what's the maximum value, we're gonna stop at 6.5 because we don't want to include negative area. That would bring our value down. So we know that from 3 our value is negative 2. So negative 2 plus the integral from, and we always have to start at 3 because that is where we know what our value is, right? Since it tells us that g of 3 is negative 2, then we have to start at 3 since we know it's negative 2 there. So from 3, and careful, from 3 to 6.5, not 7, right? Because if we do 7, that would include some negative area, which would then mean that we don't have our max. So from 3 to 6.5, 3 to 6.5. And then we have f of t, right? Because we're looking at the graph. Okay. Now, how do we solve this? Well, it's this area under the curve, right? So, what is the area under the curve? We can split this into shapes here. Okay. Let's solve the area for this rectangle. So from 3 to 5, length times width. Length is 2, width is 1, so 2. Semicircle, the area of a semicircle is pi r squared over 2. Our radius is just 1, right? Our radius is 1. And so pi r squared is pi 1 squared pi. And then since it's a semicircle, pi over 2. Square from 5 to 6 is this s squared, right? The area. So it would just be area of 1. Area of a triangle is 1/2 base times height. Our base is 0.5. Our height is 1. So 1/2 of that is going to be 1/4. 1/4. So we get -2 plus pi over 2 plus 3 plus 1/4. Okay, so -2 plus 3 gives us 1. 1 plus 1/4 is 5/4 plus pi over 2. That is our answer. All right, given h of x equals integral from 0 to 2x minus 7 of ft dt, find the x value where h has a relative minimum. So again, remember that if something has a minimum or a max, then you're going to have to find the critical point. So h prime of x is equal to, and then remember our fundamental theorem of calculus. So we plug in our upper into t, and remember chain rule. And now we're going to see where it goes from negative to positive. But since, okay, let me just continue. Okay, so 0, right? Our h prime has to be 0, right? Because that's where a critical point is. 2 times f of 2x minus 7. Divide by 2, you get 0 equals f of 2x minus 7. Okay. When does f equal 0? When does f equal 0? So f is going to be 0. F is going to be 0 at 2. Whoops, I have the eraser on. At 2 and 6.5. But since it's asking for a relative minimum, we're only going to take the value at x equals 2 because it's going from negative to positive, right? And so we're going to say that um, 2x minus 7 equals 2, right? Because 2x minus 7 has to be equal to 2 because 0 equals, f of 2 equals 0, right? So when the inside is equal to 2, f of 2 equals 0. Hopefully that makes sense. So 2x solve for x, 2x equals 9. So x equals 9 over 2. Next question. Let g of x equal to the integral from a to x of f of t dt with the graph of f shown above, and a is a constant. Find the x values of g regarding each of the following conditions. So I'm not going to explain too much. This is very similar to the last question, but now we just have a different graph, of course. So minimum occurs when g prime of x equals 0. So that means that f of x equals 0. And obviously, it's when it's going from negative to positive, right, for a minimum. So when does f go from negative to positive? that would be at x equals 8. Then vice versa, when does when does g have a real maximum? When g prime of x goes from positive to negative, or when f goes from positive to negative. So when does f go from positive to negative? X equals 6, right? Concave up, and I'm just going to write here g prime of x greater than 0, f prime greater than 0, g double prime of x less than 0, f prime less than 0. So concave up, g prime is greater than 0, g double prime is greater than 0. So we have to find when f prime is greater than 0. When is the slope positive for f? Here and here. So from 0 to 2, and from 7 to infinity. Why infinity? Well, we have the arrow, right, on the right side. We have an arrow which indicates that the graph goes on forever. On that side, of course. Concave down, when do we have a negative slope, right? G double prime is negative, so f prime has to be negative. So negative slope is right here, from 3 to 7. Increasing. G prime is greater than 0. So f is greater than 0. F is greater than 0 right here and right here. So it's from 0 to 6 and 8 to infinity. When it's decreasing, that means that g prime is less than 0, which means f is less than 0. So that would be right here, from 6 to 8. Okay. Where does the max occur of g on the interval 2 to 9? So 2 to 9, starting right here and ending right there. So we're giving an initial condition. So every time you have an initial condition, I want you to write it down, then plus integral from that x value. You cannot do from integral from 1 to something. You can't do integral from 3 to something because you don't know what the value is at those points. But we do know that when x is 2, that g is 1. So from 2 to, well, we have to figure out the upper limit. Okay, so when do we have a max? So we see that there's a positive area. Okay, pretty much from 2 to 6, right? Because we have some negative area here, a bit of positive, but that negative area is greater than this positive area. And so we're only going to do integral from 2 to 6, f of t dt. Okay. So now I'm going to find the area. All right. So 1 plus, all right, we can either split this into some shapes or we can use a trapezoid. All right, so I just set up the trapezoid area. So remember, a trapezoid's area is width times, parentheses, L1 plus L2 divided by 2, which is right here. So 3 is our width, right? 3 is our width. L1 is 1. L2 from 2 to 6 is 4. So go up here, 1 plus 4 is 5. 5 divided by 2 is 2.5. 3 times 2.5 is 7.5. 1 plus 7.5 is 8.5. All right, given h of x equals integral from 0 to x over 2 plus 5, f of t dt, find the x value where h has a relative minimum. Alright, so let's erase all this. Relative minimum. Alright, relative minimum occurs when h prime of x equals 0, right? Same for a max. So that means that f of x equals 0. Since it's a minimum, we're going to look at the 0 where the function goes from negative to positive, which would be right here at 8. Okay? So, what we're going to do is do our fundamental theorem of calculus. So, h prime of x equals f of x over 2 plus 5 chain rule times 1/2. So that is going to equal 0, right? So let me erase this. So we're going to replace h prime of x with 0 because that is when our minimum is going to occur. Okay, times 2 on both sides to get rid of the 1/2. So 0 equals f of x over 2 plus 5. So now we have to solve for the inside. So when does x over 2 plus 5 equal 8, right? Right, because that's where 0 occurs. So we know that f of the inside has to be 8. So everything in here has to equal to 8 so that we get the 0. So x over 2 equals 3 times 2 on both sides, x equals 6. Hopefully that makes sense. Okay, let f be the function given by f of x equals integral from 1 over 10 to x, sine of 1 over t dt for 1 over 10 to 1. At what values is x? At what values of x does f attain a relative maximum? So maximum, we have to find critical points. Plug in your upper limit into the function, chain rule, which is just times 1. So we have to see where this graph right here goes from positive to negative. Positive to negative, sorry about that, positive to negative on this interval. So we have sine of 1 over x. Sine of 1 over x. Okay, and in our window, we said that 1 over 10. Whoops. 1. Okay, well, I can't type. 1 over 10 to 10. Okay. Oh, not to 10, to 1. Okay. So we know that because it's a maximum, it has to go from positive to negative. So positive to negative, I see 1 right here. So we trace, second trace, we find our 0. Use a pen to... this is taking a bit. So, okay, right here. Left bound, right bound, enter. 0.159. So we attain a 0 at approximately 0.159. Okay, we have a new question. Let h be the function given by h of x equals integral from 1 to x of 1 minus e to the cosine t dt for 1 to 10. At what value of x does h attain a relative maximum? So h prime of x equals 1 minus e to the cosine x. So we're going to find the 0 of 1 minus e to the cosine x. And then we're going to see when that 0 occurs, but it has to go from negative to positive. So y equals 1 minus e to the cosine x. 1 minus e to the cosine x. We're going to adjust our window. Window is 1 to 10. Graph. Okay. Negative to positive. So we have 2, it looks like. So I'm going to find the first one. First one is right here. Left bound, right bound, enter. 1.57. So x is about 1.570. And I'm going to find a second one. So this one is all the way on the right side, right here. So left bound, right bound, enter. 7.85. About 7.85. Hopefully this was easy to understand. All right, question 5. We have a table, it looks like. Let f be a function that is continuous on the interval 1, 5. Function f is twice differentiable except at x equals 3. The function and its derivatives have the properties indicated in the table above. Let g be the function defined by g of x equals integral from 2 to x ft dt on the open interval 1 to 5. A, for 1 to 5, find all critical points of g. So critical points of g, so g prime has to equal 0. So g prime of x, according to the fundamental theorem of calculus, equals f of x here, right? So when does f of x equal 0? Right here, right here. So x equals 2 and 4. Also, it could be when f of x does not exist, but we don't have such case in this example. Determine whether g has a relative maximum or relative minimum at each of these values. So at x equals 2 and x equals 4, we're gonna look at f to see whether it changes from positive to negative or negative to positive. So at x equals 2, from the left, right here from the left, right here, this is the values from the left. So it goes from positive to, right here, the values on the right, to negative. So we have a relative maximum at x equals 2. And then we're going to say g prime changes signs positive to negative. Okay, and then we're going to look at 4. From the left, it's negative. From the left, it's negative, and from the right, it's positive. So that indicates a minimum. Rel minimum at x equals 4. G prime changes signs negative to positive. All right. Hopefully that makes sense. C, for 1 to 5, find all x values at which g has a point of inflection. G point of inflection means that g has to change signs. So g double prime, as we know, is equal to f prime. So when does f prime change signs? Okay, so we have negative here, 0, negative, so it doesn't change signs there. Negative does not exist. Positive, we do see a change in signs. So x equals 3. And then right here, positive 0, negative, we see another change in signs. So x equals 3 and x equals 4. G double prime changes signs. Okay, almost done here. The graph of the function f is shown above. Let g of x equal the integral from 0 to x of ft dt. Find the value of g prime of 6. So first we have to find g prime of x. According to the fundamental theorem of calculus, we're going to get f of x. So g prime of 6 equals f of 6. F of 6 is equal to negative 1. Sorry, not negative 1. It's negative 2. Find the value of g double prime of 6. So g double prime of x equals f prime of x. Okay, well, we're going to look at the derivative of 6 right here. Well, we know that the derivative cannot exist if we have a corner, right? Because our LHD and our RHD are different. And so, the derivative does not exist, which means that g double prime of 6 does not exist. All right, last one we have, the graph of a differentiable function g is shown above. If h of x equals integral from 0 to x, g of t dt, which of the following is true? So we have a comparison here between h prime, and h double prime. So h is the area under the curve. Area under curve. H prime is g of x. H double prime is g prime of x. So from 0 to 4, right? H of 4 is the area under the curve from 0 to 4. So from here to 4. So right off the bat, we see a huge negative area because our area is negative. It's below the x-axis. So h of x is less than 0. H prime of 4 is equal to g of 4. G of 4 is right here. That's going to be 0. So h prime, and I should say rather h of 4, not h of x. H of 4 is less than 0. And h prime of 4 equals 0. Then h double prime of 4 is equal to g prime of 4. So what is our slope here at g prime of 4? Our slope, we have a tangent line here that is positive. And so we know that h double prime is greater than 0. So our order is h of 4 is less than h prime of 4 is less than h double prime of 4, which is our first answer. So I hope this lesson was informative. Please let me know if you have any questions, and I'll see you in the next one. Take care.